Okay, let's just get started. So, anyway, we existed in this world of fire resistance until probably the early 2000s, when the collapse of the World Trade Center reinvigorated, our need to understand the problem. And people started rethinking, if we were doing things right or not. Now, there's been a real true transformation in the way in which we look at this problem in the last 20 years. And, but nevertheless, it is still, very much constrained by all this old way of thinking. So there's a number of different issues that are still anchoring us, to the way in which we used to think before. Now, this is why it is quite important to revisit these things in the context of their history, because if you don't revisit them in the context of their history, you don't understand why we are so constrained. So the fact that we created this split so early on implied that professions didn't really have the basic competency to be able to communicate appropriately. And in a similar manner, the way in which we try to solve the problem later on still emphasize some of those biases, that were carried from history. Now, what I'm going to be talking about is the compartment fire framework, and the compartment fire framework is a perfect example of that, because it stems from the fact that historically buildings were fully compartmentalized. Every room was a box, and as such, nobody was too bothered by the fact that we make requirements to compartmentalize buildings. So we constructed a whole framework of knowledge under the acceptance that the building will be compartmentalized. That was very consistent with the concept of fire resistance. So it was linked to the roots, and everybody was comfortable following that path because buildings were compartmentalized and nobody perceived that as being a very onerous kind of situation. And in the cases where compartments start getting lost, then the knowledge base didn't exist to identify that we were making a mistake. And our framework was collapsing because we didn't have walls. Okay? So the existing framework dates originally from the 1940s, 1950s, and the first individual that comes into the picture is this gentleman here called Kunio Kawagoe. Now, what is Kunio Kawagoe? There is a volume of Combustion Science and Technology that was published in the mid-80s in celebration of the retirement of Howard Emmons. Okay, Howard Emmons had been a professor at Harvard, and basically he is the father of modern fire safety. Okay, and as we were talking about a couple of days ago, his last student is Arvind Atreya. Arvind Atreya is a professor at University of Michigan, and we have a representative of that clan here sitting in the room. Yeah, my supervisor did a postdoc with Howard Emmons, and everybody thought that Howard Emmons was the greatest man on earth. And Howard Emmons belongs to the same group as Kunio Kawagoe, and when he retired in 1986, there was an entire volume of Combustion Science and Technology that was dedicated to the retirement of Howard Emmons. He was asked to write the final chapter of that volume, and a professor from MIT, Hoyt Hotel, who effectively is the name that the Combustion Institute gives to the biggest award that they have, which is a Hotel lecture. So the opening session of the Combustion Institute is the Hotel lecture. So Hoyt Hotel used to work on fire, and he was asked to write the introductory chapter. Okay, so in the introductory chapter, Hoyt Hotel talks about how fire research started in a scientific way. And it was quite interesting because it was a product of Second World War. So effectively, Howard Emmons in the United States, Philip Thomas in the United Kingdom, and Kunio Kawagoe effectively were employed by their respective governments to figure out what was the most efficient way to destroy the fire resistance framework. So in other words, they recognized that it was much more demoralizing to destroy an entire city because of the spread of flames with the subsequent collapse of buildings and everything, than actually just throwing a bomb. So what they were trying to do was to basically design mechanisms by which they could exceed the conditions that were protected by this fire resistance framework. This was so over-dimensioned that effectively it was almost impossible to destroy these buildings. So what really happened was that they had to put an enormous war effort in trying to do that. So while in the United States, right next to the Manhattan Project, there was an entire city built on Japanese standards so that it could be consistently destroyed. In Japan, they had cities built like the United States so that they could do exactly the same thing. And in the United Kingdom, they were doing the same thing with German cities. And of course, the Germans were doing exactly the same thing. This is how Theodor von Karman and people like that are part of the whole story. So effectively, there's a lot of this going on at the time. And what happens is that at the end of the war, all this starts becoming public. And everybody starts interacting and exchanging the information. And among the information that was being exchanged, there was the work of Kawagoe. So after the war, it took him about 13 years to finally put all the studies that he had done regarding fires in compartments into a paper encouraged by this other individual called Philip Thomas. So Philip Thomas worked at the Fire Research Station in the United Kingdom and effectively encouraged Kawagoe to put all his data into a paper. Now, then Philip Thomas took another set of years, about 10 years, to put together this compartment fire framework as a theoretical concept. And he used all of Kawagoe's data to fundamentally validate the model that he had put in place. Okay? So Thomas became the name behind the compartment fire framework because he was the one who intellectualized it and turned it into something that was physically tangible. Okay? Now, then came Tibor Harmony. And Tibor Harmony is the black sheep. So, on Monday and Tuesday I was picking on the Brazilians, but now the Brazilians went to New York, so today I'm picking on the Canadians. And Tibor Harmony, was the head of the Fire Research Lab at the at NRC in Canada. And effectively, he had a completely different vision and is very much related to what we were discussing earlier. So Thomas took all the data from Kawagoe and then basically said, okay, I can create a theoretical framework that describes this type of fires that occurs when the windows are of this size, when the compartment is of this size, and when everything is compartmentalized. So the Fire Research Station, being a government organization in the United Kingdom, enabled him to legislate. So effectively, they start developing codes that were compliant with the framework of Thomas, because Thomas's principle was, I can calculate this. So because I can calculate it, then if you design the building the way I want it, then I can tell you what the answer is. And that answer is very consistent with the fire resistance framework, so you can still keep using your fire resistance concepts, okay, if you design the rooms this way. Okay? So that entered straight into the codes. And for a long period of time in the United Kingdom, you had very strict prescription on what is the maximum size of a compartment, on what had to be the barriers, on the dimensions of the windows in relationship to the height of the compartment. Everything was completely structured around the idea that if that is the case, I can calculate the answer and then you can keep using your furnace. Okay? So Thomas was incredibly conservative, but he also had the power to encourage government to be able to do things the way he felt it was appropriate. So he became probably one of the biggest landmarks in sort of post-war fire research in the United Kingdom and influenced really, basically a very significant part of the world. A place where they couldn't get to was the United States and Canada. Now, in this particular case, the Canadians were supporting the Americans in trying to look into something completely different, which is in the United States, buildings were much newer, and therefore the concept of an open floor plan, was a much more prevalent concept. And therefore, there was an enormous unwillingness, to try to compartmentalize, okay? So Harmony, had a completely different vision of the problem. He basically looked at all of Thomas's data. He looked at the framework that he had put in place. And he said, look, your framework analyzes the most onerous of cases, which is this typical compartment that you've designed. That's the worst case scenario, okay? So if I analyze the problem like you did, all the other problems, the traveling fires, the localized fires, all these things, according to your data, in most of the cases, are lesser of a problem, okay? So I'll still stick to your framework, okay? But I will extend its application to the open floor plan office, okay? So that was the principle. So his argument was, Thomas's framework analyzed the worst case scenario, okay? So if the other scenario of the open floor plan was lesser, okay, then if I stick to Thomas's framework, I calculate as if it was more, less would still suffice, okay? So that was Harmony's position, very engineering approach. So we had the opportunity several years ago. The fire research station became the building research establishment with the years, and then they got privatized, and at some point, as all private companies, they start sort of trying to optimize expenditures, and the first thing they got rid of was the library. So effectively the library was going to be thrown away, and we had the fortune of being able to get a truck, driving all the way to BRE, and literally collecting the integrity of the library of BRE, which still is at the University of Edinburgh, I presume. I don't know if they've thrown it away already, but it was still there in the roof.
I know it's been picked up by the library.
Yeah. So effectively, the library went in there. Now, there was a very interesting thing. So a couple of the students, I had mentioned John Gales already and Agustin Magdalani. So these two students discovered a cabinet, and that cabinet in the drawers, had all the papers of Philip Thomas, okay? And in one file that said Harmony were all the exchanges of correspondence between Philip Thomas and Tibor Harmony, okay? So if you open the papers, and I don't know where they are, somebody, I think Gail stole them and brought them back to Canada. He's Canadian. So anyway, so basically you will open the documents, and there are the original papers typed with a typewriter that Harmony had mailed, some of them in the envelope with the postage and everything. He had mailed to Thomas with a very polite letter saying, Philip, I would like you to look at this. I've extended your framework and blah, 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 blah. So then you will look at the paper, and there were all of Philip Thomas's annotations. What an idiot. This is completely wrong. This is ridiculous. He destroyed the papers and sent him his comments. So then Harmony will write back and apologize for having made these mistakes and blah, blah. And it kept going back and forth, back and forth, back and forth, but you can realize the mindset. So what was going on was that Thomas kept saying this, yeah, fair enough. Most of the cases are less onerous than my framework. But what about this, and what about this, and what about this? My framework doesn't apply to the open floor plan. So I have not been able to explore all the possibilities, but I have enough evidence of cases where it's a lot worse. Okay, so Harmony will reply, and I said, yes, but those are only a few. And Thomas said, well, that's sufficient. You cannot design knowing that this is going to be potentially a worst case scenario than the one I have in my framework. So if you use my framework, you're missing this point. And this is where the stroke of genius came up from Harmony, okay? So Harmony said, okay, fine, I accept that. What are we going to do to make sure that the probability of this dot is so low that it doesn't matter? What do you think he did? You have the framework. It describes 99 out of 100. is worse than 99 out of 100, but there is one that is worse than the framework. Okay, he accepts that that case could possibly happen and we have no theory to predict it. Nevertheless, we can still design with the framework and ignore that point if we manage to make its probability negligible. How do we do that? Can't believe the silence.
You can legislate that case out of existence.
Well, you can't because you cannot predict it, so you don't know when it happens. And that was Thomas's argument. It's like you don't know when it happens. Well, you could do that, okay? But the problem is because we didn't have theory for this, we didn't know how bad it could get. We knew it was rare events because Thomas had done tons of tests and he had collected all of Kawagoe's tests, okay? So we knew it was rare, but we didn't know why or when it happened or how big it was. So Harmathy's point was, let's reduce its probability to a point where it becomes negligible. And the question is, how do we achieve that?
Did they make it more expensive to do this kind of layout?
How? What expense can I add to reduce the probability of that happening?
Is it possible to add like a layout?
No, no, you cannot tax the physics. You have a physical process that you want to eradicate or at least make its probability as low as possible.
Can you use safety factors?
But safety factors of what? You don't know the physics. Yep.
This whole time you've been saying the framework is the issue, so you just change the framework.
No, you can't because you don't know. You don't have the knowledge to do it. Okay, this is all he could predict. He couldn't understand what was happening in this other regime.
Just exception? One exception is...
Yeah, but nobody is going to accept that exception that says, I'm going to kill everybody. Okay?
We keep doing burning stuff till we have that exception and figure out the probability.
No, no, we tried to do that and it never worked. They couldn't figure it out. You throw water to the fire. Sprinklers. So Harmathy's solution was the way we reduce the probability of this event happening is we put sprinklers in all open floor plan offices. If the surface area exceeds Thomas's criteria, use sprinkler.
Is it real?
Yeah? So what happened? North America went sprinklers like crazy. So you put sprinklers everywhere. You have them there. You cannot see them. They're covered. Europe were compartmentation. You have sprinklers nowhere. And it all stemmed from an intellectual fight between Philip Thomas and Tibor Harmony. Once the whole thing was done, Howard Emmons came and picked up the pieces. So he basically created this computer model and all the stuff where he structured all this knowledge and basically made it an engineering tool. Okay? So how does history reward people? So if you go to the International Association for Fire Safety Science, the biggest honor you can get is the Philip Thomas Medal. Okay? And the Philip Thomas Medal is for exceptional contributions to the theory of fire. Okay? You can get the Kawagoe Medal. Okay? And the Kawagoe Medal is for exceptional contributions to the understanding of fire. Okay? Or you can get the Howard Emmons Lecture and Medal, which is the top honor you could possibly get, which is for your exceptional contributions to fire. Okay? What happened with Tibor Harmony? He retired from NRC, he became a science fiction writer, and he became a multi-millionaire with a bestseller book on science fiction, some Martians that came to Earth or something like that. Yeah, history decided to forget Tibor Harmony. He doesn't exist. It was only about 4 years ago that one of my former associates, who is an editor of a journal now, after all this thing had happened, decided to resurrect Tibor Harmony and award the Tibor Harmony Medal for the best paper in this journal to a young scientist. Okay? It's sort of rebirthing from the ashes. Okay? So that's Fire Technology awards the Tibor Harmony Medal to a paper written by a first author that is a young scientist. Okay? Until then, Tibor Harmony was buried. I gave a presentation in the International Association for Fire Safety Science a few years ago, and I decided to ask the question to all the fathers of the field. It's like, why did you decide, to ignore Tibor Harmony? And there was silence. And at the end, when I walked out, one of them, with his stick and he's walking, grabs me, man in his late 80s, grabs me from the arm. He says, irresponsible. That's why he was irresponsible. But needless to say, the impact of Tibor Harmony was extraordinary. So effectively, all the concept of putting sprinklers in open floor plan offices, all the sort of restrictions on maximum sizes for the use of the compartment fire framework, all that stemmed from the knowledge of Tibor Harmony. So Tibor Harmony effectively was the real true engineer in this whole process. Nevertheless, he took risks that the other ones were not willing to take. So at the end, we have two schools of thought. One of them is compartmentalization. The other one is basically sprinklers as a way to get rid of that data point that I don't like. Okay? So that's basically it. So what is the premise of the sprinkler? Is that if the sprinklers work, the fire will never get to those conditions. So in other words, you have eliminated the problem from the source. And you have, if everything works out fine, in an ideal scenario, 99.9% chances of achieving that objective. Okay? If everything goes pear-shaped, you can say that the lowest reliability of a sprinkler system is about 75%. Okay? So one way or another one, you have eliminated at least 75% chances of having that scenario. Okay? If that's good enough, that's a different story, but nevertheless, that's the way we created two different schools of thought that have completely transformed the way in which we design buildings. Okay? So,
What were the year ranges that you have there?
sorry?
The previous slide, the year ranges.
Oh, the years. So 1958 is the paper published by Kawagoe. Philip Thomas published 4 papers in 10 years between 62 and 72. Tibor Harmony published his papers between 69 and 76 in those 7 years. And 1976 is the year that Howard Emmons published first, which is the computer model. Okay? So those are the years in there. So anyway, so let's go back to the basics and figure out what they were trying to do. So effectively what they were trying to solve was an energy balance. So they wanted to solve the fire dynamics in such a way that you could develop a net heat flux or the boundary condition for the structure so that you could actually solve the heat transfer equation. So if you take the simplest form of the one-dimensional heat transfer equation, the transient heat transfer equation, and basically the boundary condition at the surface is going to be this Q net, this becomes the goal that we're aiming at. So that's what we want to obtain. So once I put the boundary condition, I can solve the energy equation, and with the energy equation, then the structural engineer can perform a structural analysis. So that's the basic principle. So at the end, the goal is to obtain this Q net. So this is really what we're aiming at, okay? And for that purpose, we are going to try to solve all the energy balances within that compartment. Now, the problem is that as all fire problems, the moment you start digging into, you realize that it's a little bit more than what you thought. And many times, we have to chew more than what we can. And this is exactly what ended up happening at this point. So basically, you have the easy term, which is the energy entering the control volume, which is going to be the mass of airflow coming into the control volume times the specific heat times the ambient temperature. That's the energy input from the air. Then you're going to have the energy generated, which is the heat release rate, again, burning rate multiplied by the heat of combustion. Okay? Now, then you have the energy that leaves the control volume, but in this case, the temperature doesn't have to be constant. So effectively, you're going to have a temperature distribution in Y and Z leaving the door, okay, times the specific heat, times a flow rate that also is going to vary along the opening. Is that okay? So you have to have a double integral of the energy that is being advected, through the door, plus the area of the opening multiplied by the radiation that is being expelled. So effectively you have a hot room and is radiating out. So you're losing energy through radiation and you're losing energy through advection or a mass that is taking energy outside the compartment. So as you can see, because you have distributions of temperature around the compartment, effectively you have to solve this as a function of the surface area of the door. Okay? So here's energy in, energy generated, energy out. So if you do energy in minus energy out plus energy generated, that gives you the change of energy in the control volume. So there's the extra term, which is how much energy is going into the structure. So this is energy out to the structure, energy out of the compartment, energy into the compartment, and energy generated. And the difference of all those basically has to be the energy inside the control volume. Now, in this case, it's a triple integral because it's the volume of the compartment, and it's going to be the mass of the control volume, the specific heat, times the temperature of the control volume in X, Y, and Z. Okay? So if I want to do the full energy equation, effectively this is what I get. So the change of energy of the control volume is equal to the energy generated plus the energy in minus the energy out minus the energy going to the structure. Okay? So it's just a simple energy balance in concept, but an incredibly complex problem in practice. Each one of those terms is incredibly complicated to obtain and very, very, very difficult to model. It is perfectly clear that even today our CFD tools cannot model this type of compartment fire because keep in mind that we are in the ventilation limited regime. In other words, we don't have enough oxygen entering the compartment, so we have very incomplete combustion, and modeling incomplete combustion requires you to be able to resolve the flame thickness. And we don't have the capacity to resolve the flame thickness, so we cannot introduce the chemistry, and because we cannot introduce the chemistry, this is very difficult to model. Okay? Yes?
Now this is making the assumption that combustion happens only inside the compartment, not taking into account burning in the exhaust.
No, that's not making the assumption because effectively whatever is happening, my control volume is the compartment. Okay, so it could be burning partially in here. So I have not defined what this number is, and I have not defined what the completeness of the combustion is. So whatever extra is going to spill out of the compartment and might burn outside. Okay? So effectively that's the problem. Now very rapidly it was clear that you could not do that. Okay? And even as I say, until now, you can actually not do that. So I was talking about, Hoyt Hotel's paper at the beginning, talking about the history of fire research and talking about all this idea of Thomas and Kawagoe and how they started, this field of science, if you want to call it. So that was all in the first paper by Hoyt Hotel. In the final paper by Howard Emmons, is the next 100 years. And according to him, the full solution of this energy equation will not be solved until 2050. So that was Howard Emmons' prediction. I'm more and more confident that it's going to be a lot longer than that. Okay? And but when he wrote that in 1986, he put it as 2050 as being the moment where he expected that we were going to be able to solve this energy equation correctly. Okay? We'll see what history tells us when we get there. Well, probably I won't get there, but so basically the different characteristic timescales of the structure and the fire do not require, fortunately, that precision, because as I've been telling you, the combustion processes are incredibly rapid compared to the heating of the structure. So averaging in time is something that is actually very appropriate in this case, because all the fluctuations of combustion are somehow irrelevant to the heating of the structure, because the structure heats up very slowly. So effectively, the structure is an averaging process, because you're damping, the impulse from the fire, and all the changes are happening in the fire being integrated into the structure. And because the structure heats up so slowly, that allows me to make massive simplifications in the problem. Okay? So we looked for a simplified formulation, and that was Thomas's compartment fire formulation. Okay? So basically, this is a Thomas compartment. So this is how a Thomas compartment looks. So it has a restricted area. Okay? So this will be the restricted area of the compartment, and it has a restrictions on the window sizes. Okay? And effectively, it's a very, very simple, very small box. Okay? Cubic, more or less, in nature, and really a very simple formulation that was very consistent with Victorian era type of buildings. So Thomas describes two regimes. So, and it's really interesting, actually, the way those regimes are described. So if you look at the picture in the left, effectively you have a small compartment, a small window, okay, which basically allows for all the smoke to fill up the compartment, okay? The moment the smoke fills up the compartment, you reduce the velocities in the interior of the compartment almost to zero, because you have smoke in there that doesn't allow the flow to move inside. And all the exchange of mass happens at the window or at the door. So what you have is a compartment that effectively is filled up, with smoke. And because it's filled up with smoke, so this compartment is completely filled up with smoke to the point that the velocities here approximate zero. And all the exchange is happening at the door. Okay? The velocities will die out very rapidly, and effectively you get all the exchange of mass happening at the door, basically on hydrostatic pressure. Okay? So you have low density here, high density here, and that enables a pressure difference between the inside and the outside that creates this exchange of flow at the window. And because the velocities go to zero, the fluid mechanics disappears. Okay? So this is purely a hydrostatically controlled problem. Okay? So all that is controlling the problem is what is happening at this point at the door. Okay? Now, if I open the window and make it much bigger, then what I have is a completely different problem. Here is my fire. The fire acts as the pump. Okay? And I get flow coming in, goes up, hits the ceiling, creates a stagnation flow, and basically goes out. The velocities are much greater than zero all over the compartment. So this one is hydrostatic. Okay, velocity is equal to zero, and this one is momentum driven. Is that okay? Now, the problem is that if it is momentum driven, okay, and you have this very large velocity that is going in and out, you have to solve the fluid mechanics. So the fluid mechanics are incredibly complex in this particular case, because you do have a buoyant flow that is driving, confined by this compartment, a flow field that is incredibly complex. That flow field is determining the characteristics of the combustion, and the characteristics of the combustion are going to determine the total heat transfer to the structure. So this problem Thomas deemed as unsolvable. And he says, there is no way I can solve this problem. This one, I can. Okay? The moment the velocities go to zero, I don't need to solve the fluid mechanics. And I can treat the problem as purely an energy balance within a static control volume, where the energy that is being created now is purely controlled by the hydrostatic supply of oxygen into the compartment. Keep in mind, I have excess fuel. Okay? So all the oxygen that comes in gets consumed. So the heat release rate is going to be a function of how much oxygen I can get in. Okay? So basically, I can calculate the heat generation directly by doing a hydrostatic, a Bernoulli at the door. Okay? Here, I cannot calculate the heat generation because the oxygen is entraining so much that I have no idea how much air I'm bringing, and I have no idea how much fuel I'm burning. I have to calculate the burning rate. I have to get all these things. So here, there is no way I can actually calculate the heat generation. While here, it is just a matter of how much oxygen I'm bringing into the compartment. So this problem is infinitely simpler than this one. Okay? So that's exactly what Thomas did. So basically, Thomas and Helseden, this is the main paper of Thomas. He said, well, let's split the problem in two. We're going to have regime 1 and we're going to have regime 2. Regime 1 is perfectly solvable. I can give you an answer to that problem. Regime 2, I have no clue. You shall not build like that. Pure genius, no? I mean, seriously, having the power to do that, to basically saying you shall not do it because I don't understand it. I mean, it's really a powerful message.
So
Yes.
for the case 1 that we can solve, isn't it like the flashover condition that we are avoiding?
No. So this is all post-flashover.
Oh, okay.
So basically, this is a fully developed, huh?
Because you said it's full, like it's fully like the smoke is accumulated all the way down.
Yeah. Yeah, so you fill the compartment because you flashed over, so you have basically fuel all over the place. Okay, so they're both fully developed. Now, many times this one is confused, you know, with a growing fire, but it's not a growing fire. Everything has ignited. So it is flashovered. It's just that because it's momentum driven, okay, it's creating such a flow field that it still has two zones, the hot zone and the cold zone. But the hot zone is radiating so dramatically that effectively you are post-flashover. Okay, if you put any solid in there, it will ignite. Okay, it is just simply a different regime that is momentum driven. So the difference between the two of them is that one is hydrostatic driven and the other one is momentum driven. That's the difference. You don't know what the stoichiometry is here, so I don't know if it's under-ventilated or over-ventilated. I have no idea, because I cannot recreate the fluid mechanics. This one I know, okay, that is fuel rich, because I can calculate how much oxygen gets into the compartment. But this one I have no clue. Is that okay? So effectively those are the two regimes. So this is a perfect example of a fire in the regime 1. So, if you look at it, it almost seems that it's not the case, no? Because obviously what Thomas is doing is an approximation, and air has to go in, and there is going to be an area of clear of smoke in the bottom, and there is going to be a gradient of temperatures in there, and there's going to be all sorts of things, and smoke is not going to be all over the place. But basically what he's saying is you can approximate that as such. Okay, so that's basically the approach. But this will be a typical case of a regime 1 type of fire. Okay?
Sorry, what was he like solving for?
Sorry?
He was solving for some.
I haven't got there. I'm going to get to the solution. So I'm just explaining what the two scenarios are. Okay? And then I'll explain to you what he was solving for. Okay? So what are the assumptions that he's going to make for regime 1? So before we can solve it, we have to go through the assumptions. Okay? So his first assumption is he's saying, well, the heat release rate is defined by the complete consumption of all oxygen entering the compartment, you know, and its subsequent transformation of energy to energy. Is that okay? So effectively he's saying it's fuel rich all the oxygen that gets into the compartment will be consumed and it will be turned into energy. Is that okay? So effectively that changes the problem of the heat of combustion to be the heat of combustion per kilogram of oxygen. So all of a sudden this number is 13.1. Is that okay? So you have 13.1 megajoules per kilogram, the ambient oxygen concentration and the mass flow at the opening. Okay? So that gives me kilograms of oxygen per second multiplied per joules per kilogram of oxygen gives you joules per second, watts. Is that okay? So the heat generation then is defined by this very simple expression. Okay, you're consuming all the oxygen, the concentration of oxygen inside the compartment is assumed to be 0. Okay? The second, so basically what does that do for you with regards to the energy equation? It eliminates the need to define the oxygen concentration in the outgoing combustion products because it's 0. Is that okay? All the oxygen is consumed, nothing is coming out. It eliminates the need to resolve the oxygen transport equation within the compartment because you're turning everything straight into energy. Okay? It limits the analysis to scenarios where there is excess fuel availability. That is a constraint, but it is accepted that in this regime 1, that's what is happening. The chemistry is fast enough to consume all the oxygen transported to the reaction zone, so you're assuming very strong fire, very strong combustion reaction, very fast chemistry. You're consuming all the oxygen, nothing gets out. Okay? The control volume acts as a perfectly stirred reactor. In other words, he's assuming that everything is homogeneous. So while we know that there's some temperature gradients and some concentration gradients, he is effectively assuming everything is homogeneous. So I'm dumping the energy into the compartment, shaking it like a perfectly stirred reactor, and it's an homogeneous temperature distribution. Okay? So, and the heat of combustion is assumed to be an invariant. You know, the completeness of combustion is independent of the compartment. So effectively, he is not doing incomplete combustion, he's doing complete combustion and thus having the worst case scenario. Is that okay? You could put a combustion fraction efficiency or whatever if you want, but the reality is that he stayed conservative and he said, let's make complete combustion. 13.1 is what we're putting in there. Okay? So the second assumption was that radiative losses through the opening are assumed to be negligible. Therefore, Q out is treated as an advection term. Okay? In other words, all you get is convective flow coming out because you're assuming that radiation out of the door is actually negligible. Interestingly enough, Harmony didn't believe Thomas. And he went and did a whole bunch of experiments to prove Thomas wrong, and he ended up showing that Thomas was right. You know? And he published a really nice paper where he showed that the total energy release is about 3% goes away on radiation. Yes?
So this is because you have a small opening?
Yes, so you have a very small opening and the processes happening in and out are so rapid that effectively you're generating a massive amount of energy. Well, in reality, if you look at it, you have a small opening and your radiation is a fixed temperature times an emissivity of 1 times sigma T to the 4th. So it's a fixed number. So if I generate 10 times more energy, I make this relatively smaller, no? So you're generating energy so rapidly that effectively your losses due to radiation are negligible compared to everything else. Okay? So this had to be proven, and it had to be proven by experiments, and then that's what Harmony did. So there are no gas, solid phase temperature spatial distributions within the compartment. In other words, he assumes the whole compartment is at the same temperature. So there's only one solution to the problem, which is the temperature of the compartment. So what he's going to try to obtain is the temperature of the compartment. If you have the temperature of the compartment, then you can put a heat transfer coefficient and find your heat flux to the structure. Is that okay? So the solution to this will be what is the temperature of the compartment. Okay? And there's only going to be one because it's not spatially resolved. It's a perfectly stirred reactor, everything is the same temperature. Is that okay? The mass transfer through the openings is governed by static pressure differences. In other words, it's Bernoulli. So this is an orifice plate correlation that basically says the velocity is proportional to the height of the opening, okay? And the velocity multiplied by the area gives you the flow rate, And then the density and all the other terms, gravity, they all go in this constant C. Is that okay? So if you do Bernoulli on an orifice plate, you're going to get that expression with a bunch of constants, and all the constants go into this term C. So basically, he evaluated the C, and they came up with values that were appropriate. And again, there was another exchange between Thomas and Harmony into what should be that value of C. And there were different values that were proposed, both by Harmony and for Thomas, but at the end, they actually converged on a value of 0.2. Okay? So effectively, those are all the assumptions. Yeah.
How do you categorize which is regime 1 and which is regime 2? Like, is there a relative size of the opening? Because I'm assuming the 3% was tied to a special.
Yeah. So this is all regime 1. Okay.
Yeah. How do you say it's regime 1 versus?
Well, I'll show you. So they're basically gonna come up to the conclusion of what is regime 1 when the theory doesn't work. So you put the theory, you put the experiments, and when the experiments deflect from the theory, you say that's the separation of the two. Okay? So, because keep in mind the arguments between Thomas and Harmony happened after Thomas published his paper. So he already had defined regime 1 and regime 2, so when Harmony went and validated the radiation, he was doing it only for openings that corresponded to what Thomas had labeled as regime 1. Okay? So, this is what he did. So basically, this is your energy equation now, according to the simplification. So basically, I have a single temperature, that's the temperature of the compartment, that represents the whole temperature of the control volume, and the control volume will be this entire thing. Okay? So it's the mass of the control volume times the specific heat times the temperature. And so the change of temperature with respect to time, the energy of the control volume change with respect to time, is the heat generation plus the heat in minus the heat out minus the net that goes to the structure. Is that okay? So the first thing that you can simplify is that Q in is much smaller than Q out, because Q in is fresh air coming at ambient temperature, so it's mCp T infinity. Okay? Now, whatever comes in has to come out because of conservation of mass, so the M in has to be equal to the M out. So M coming in has to be equal to M coming out, and therefore the only difference between Q out and Q in is the difference in temperature between the hot gases and the cold gases. Yeah?
Sorry, but you have a fire in there, so you have like some solid material going eventually to the gas phase. So does your mass of gas exiting, is it perhaps slightly higher than?
Yeah, but you're too sophisticated here. We're neglecting that. I mean, keep in mind, like where we're coming from. So we're coming from 10,000 times more air, okay, than the fuel that you're producing. Here we are, let's assume that we're slightly below stoichiometric. In other words, it's rich. You still have all the nitrogen comes from the air. So the mass of the air, because of the presence of the nitrogen, is still much bigger than the mass of fuel that you're producing. So generally, you will ignore the amount of fuel that is entering the compartment. Is that okay? So even if you were stoichiometric, the mass of air will always be a lot bigger than the mass of fuel. Okay? So basically then, these two masses are the same. So the difference between the two terms is effectively the difference in temperature between the hot and the cold. So your Q out has to be bigger than your Q in. So you can neglect your Q in because your Q out is much bigger. Okay? So the mass in is equal to the mass out, so we're going to call it M, and this comes from the orifice plate application of Bernoulli. Okay? The heat generation is the mass that is coming in or out, multiplied by the ambient oxygen concentration times 13.1. So now we can calculate this term, done. Okay? Now the Q out is the mass times Cp times Tg max, and then he approximates the heat transfer to the structure by means of just simply a linearized version of conduction. So this is the area of the room through which heat is being transferred, multiplied by the thermal conductivity times the linear version of Tg max minus T infinity times delta, which is the thickness of the wall. It's cold on the outside, it's hot on the inside, and he does a linear heat transfer analysis, okay? Now, this is very important because we need to understand what is A. A is the area through which heat can be transferred. So, what is physically A then? Yeah.
The area of all surfaces?
Yes?
Yeah.
Minus? Huh? Minus the openings, because the openings are accounted differently. So it's the area of all the surfaces minus the openings. Now, are you losing heat through the fire? No, so the fire is burning at the bottom, no? So it's minus the floor. Is that okay? So this area is the net area of Thomas, and effectively is the entire area of the compartment minus the openings minus the floor. Okay, because the floor is where the flames are, so no heat is being lost to the floor. You look with a very skeptical face, Tarek.
Yeah, no, sorry, I missed the reasoning there. I don't understand that.
Okay, so this wall
Yeah.
is colder than the fire. So you're going to lose heat through this wall. You're not going to lose heat through the openings because I already accounted it as a flux. Okay, so basically it's energy in, energy out. There's no surface through which there's conduction in there. It's just basically convective. So I can take from the total area of the compartment, first of all, I can take the openings out. Is that okay? Now, if you look at the floor and the floor is all burning, keep in mind this is post-flashover. Who is hotter, the floor or the fire? I mean, the fire is emerging from the floor. Okay, so he's assuming that there is no heat losses to the floor because that's what's burning. Okay, and he's saying, well, we'll subtract then the floor because this is where the energy is coming from. Okay, so effectively this area becomes the total area of the compartment minus the openings minus the floor.
Yeah, I understand.
Okay? Yes?
Couldn't that same argument be used to say that the walls are burning?
Of course, if the walls were burning, that would be the case. But in this particular case, he's designing a conventional room where your fuel is in the floor. But clearly, like for example, this has been extended to timber buildings. Okay, where you actually have the walls that are burning, in which case you will have to subtract the wall. Is that okay? Yeah.
Is the argument through the floor because of the fire or because there is
Yeah.
nowhere to lose the heat to? Because I'm assuming if there was fire on the wall, there would be heat loss through the wall.
No, because you see, look at it, look at it. The fire is right in front of the wall. Okay, so yes, you're losing heat, but that's what's producing the fuel. But once you are in the controlled volume, this surface is supplying energy. It's not losing energy.
Yes, but it's going to be hot enough that it's going to create a high gradient, temperature gradient between the surface of the wall, which is burning, and the outside surface of the wall, which is at very low temperature.
Yes, but that's outside my control volume. Okay, so if I look at my control volume, so if you take your control volume, this is your control volume, okay? This surface of the control volume is losing heat. This surface of the control volume is losing heat. This surface of the control volume is losing heat. This surface of the control volume is putting heat in. That's where my heat generation is coming from. Okay, that's the way he frames it. And of course, the flames are somewhere around there, okay? But his control volume is defined outside the flame. Keep in mind, there's no reaction, there's nothing. He's just basically putting energy into the control volume. He knows what the quantity is, and that energy is coming from this surface of the control volume. And of course, there is going to be behind the control volume, there will be another control volume, where this flame actually is losing heat this way, is producing fuel that way, okay? And there's going to be heat losses to the back. But that's a different control volume. Is that okay? Yes.
Yeah, I was going to ask why can't we extend our control volume down if we're concerned?
Of course you can. You don't want to. It's too complicated. Just keep it simple. Keep the control volume close in there so that you can actually have a box of gases that is getting energy. That's all he wants.
Right, yeah.
It's pretty straightforward. You can complicate this as much as you want, but that's not the point. Okay? The point is to make it simple. Okay? So don't lose focus, okay? We want the temperature of the gas. We don't care what's happening with the flame, okay? So here we have all our terms. So the first thing he says is, I'm going to make the problem steady state. Why does he make it steady state? Because he says that effectively I can average the combustion endlessly, and it doesn't really matter. The worst condition will be when the structure has reached its steady state. That will give me the hottest temperature of the fire. So if I use the hottest temperature of the fire to do my heat transfer, is a worst case scenario. Is that okay? Are we happy with that? The only reason why he's making it steady state is so that it is a worst case scenario. Okay? Once again, it is not real. You're going to be transferring heat at a much lower rate through the entire heating process, but at the end, the maximum amount of heat that you're going to transfer is when effectively you artificially insulate your compartment, because the whole walls are now steady state. I get the maximum temperature of the compartment, and if I use that as a reference to calculate my entire heat transfer, I will get the worst case scenario. Is that okay? So there it goes. Term goes away, becomes 0. Then the Q in goes out because Q in is much smaller than Q out. And then the equation that he needs to solve is this. Is that okay? So this gives you this as an answer when you substitute everything, and I'll show you what the different terms are. So effectively, all I'm doing is I substitute the heat generation, which is going to be the mass times the concentration of oxygen times the heat of combustion. I know that. I'm going to substitute the Q out as being the mass times the specific heat times the maximum gas temperature. Okay, so the temperature of the gas. Okay? And then the Q net, I'm going to substitute it as the Thomas area, the net area, times the thermal conductivity, times T gas minus T infinity over the thickness of the wall. Okay? So I plug all this here, and I solve for the temperature of the compartment. Is that okay? When I solve for the temperature of the compartment, this is where the genius comes up. Okay? So effectively, you solve for the temperature of the compartment, and you get two characteristic temperatures. Okay? And in a way, this is what effectively results in the elimination of combustion of the problem by understanding what you're doing. So, the two characteristic temperatures. One is TF. What is this? The adiabatic flame temperature, no? A very simplified version of the adiabatic flame temperature. The maximum possible temperature you could get. Is that okay? So basically you're taking all the energy and you're converting it into temperature. So if you divide the CP, you get the maximum possible temperature you can get. Is that okay? So this is the adiabatic flame temperature. Now, what is this? So basically, this is what he calls the conduction temperature. And the conduction temperature effectively tells you this is the energy that I'm generating. Okay? And this is the energy that is being conducted. So it's telling you what fraction of your energy is going through the walls as opposed to staying in the compartment. Okay? So, for example, if you have a huge thermal conductivity, okay, then what happens is that your conduction temperature goes to 0. Is that okay? So if you have an extremely large area, a lot of energy goes down the area, your temperature goes down to 0. Is that okay? If you get a big opening, still within regime 1, but if you get a big opening, that means that you're producing a lot of energy, so this conduction temperature goes up. Okay? So every single parameter becomes meaningful. Now, if you look at it in this equation, so if your thermal conductivity is very low, okay? Therefore, everything is insulated. You're not losing any heat through to conduction. This number becomes very high, no? Is that okay? So if this number becomes very high, this term becomes 0. So you get in the numerator 1. If this value is very high, this term becomes 0, this becomes 1, you get 1 over 1. The maximum temperature is the adiabatic flame temperature. Okay? So at one extreme, you get the adiabatic flame temperature. Now, if you're losing all your energy through conduction, this term becomes 0. So if I multiply by TCD and TCD here, and I cancel the denominator, I get TCD plus T infinity, but TCD is 0, so I get T infinity on top. I get TCD plus TF, TCD becomes 0, you get TF in the denominator, TF cancels with TF, and effectively you get that your maximum temperature is T ambient. So if all the energy that you produce immediately gets out through the walls, your compartment stays at T ambient. Okay? So, according to Thomas, then the theory says, if I put TG max in here, yeah. So if I put TG max here, okay, and the way he does it, he says, well, all these are constants, okay? The only variable is this. So if this term is 0, then TCD is 0. If this term is very large, then this term is very large. So this is equivalent as playing with the conductivity. This is what he calls the ventilation factor. Okay? So instead of plotting it with the thermal conductivity, he plots here A0 square root of H0 over A. Okay? So if this term is 0, you get the adiabatic flame temperature. No? And if this term is very large, you get T ambient. There's your theory. Okay? Obviously, it's going to curve towards the end because it's asymptotic at this point, but he wisely truncates it at some point. Okay? But that's the theory. Are we happy with that? And the theory depends only on one single variable, which is a ventilation factor. And that variable happens to be purely geometric. So given that it's purely geometric, for Thomas to know what the temperature of the compartment is going to be, who is the only professional he needs to talk to? The architect. Little conversation with the architect, this is the size of the window, this is the size of the room, done. 1,000 degrees. Brilliant, no? Then he can give that to the structural engineer who can multiply by a heat transfer coefficient, they get a heat flux, they can calculate the temperatures, and they can do their job if they wish to, which they don't, but you know. But in reality, problem is solved, no? I mean, it's an incredibly powerful framework. Simplifies not only the calculations, but the process. Because the architect can design freely, he only has to give you the ventilation factor. Okay? So what happens? It gets to a point where if you make this number the wrong number, okay, then what happens is that effectively you cut it off. Okay? And the data starts diverging from the theory. Harmony will claim that the theory, okay, is always worse than the data. Is that okay? But Thomas found always that somewhere in here there were a few strangler points. And they were all around here. Okay? And this is where the argument between the two of them was. Is that okay? Are we all comfortable with that? Okay? So effectively, that's the principle. So let me turn this off again. So effectively, we've created a framework, and now what he's going to do is match the framework to the data. Okay? The only parameter that matters is the ventilation factor, and this is all the data. So you can see the stranglers in here. This is the theory. This is regime 1, and regime 2 starts appearing at the point where effectively it falls down. Just one second. As you might notice, the way I put it in here, for whatever reason that I still will never understand, Thomas liked to put the inverse ventilation factor in his plot, okay, which is really annoying. Okay? So instead of putting A0 square root of H0 divided by A, he flipped it around. So Thomas used to work, with this guy called Jeff Cox, because he will never talk about this, but Jeff Cox used to be his very close collaborator, and Jeff Cox was absolutely convinced that Thomas liked to write things in a very complicated way because he had very high standards for competency. So he said that people should struggle trying to understand his work, because that's the only way he could guarantee that they were smart or knowledgeable enough. And anybody that wears a bow tie and always looks like a crazy professor, thinks in those terms apparently. But he had this whole theory about writing very complicatedly. His papers are horrible. I mean, they're almost impossible to understand. You have to literally read them 15 times before you get what he's talking about. And he will do these little tweaks of the thing, which is basically flip it around for no reason. And put the inverse ventilation factor as opposed to the ventilation factor. Yeah.
Does give nice numbers of the order of 10 instead of 0.0.
Yeah, well, you can claim that. Yeah. Yeah, so you can claim that the axis can be put in integers instead of decimal places. But I don't know. It mixes the physics, which bothers me, because a ventilation factor should be bigger when you ventilate more, not when you underventilate. So anyway, so later on, people started calling the inverse ventilation factor, which makes it even more dirty. I mean, it's just annoying when you start adding qualifiers. But anyway, so what he did was basically then fit the data to the experiments, and some of the experiments actually fall really down. And they tend to be experiments where you get these weird shapes. So if the room is a cube, it fits the data beautifully. As you start getting very elongated rooms, so if you look at the numbers here, 4, 4, 1, what that means is 4 times as long and as wide as the height. So this will be a very low ceiling room, so it's a larger room with very low ceiling, so the air cannot get in properly, the combustion is very poor, so of course you get much lower temperatures. Okay, the other ones are 2, 1, 1, 2, 2, 1, 1, 2, 1, so they're basically more or less cubic. Okay, so effectively, the more you approach the cube, the more perfect the collapse of the data is. But none of these points really goes too far out from the theoretical predictions when it comes to being above the theory. In contrast, when you drop to regime 2, on average, the temperatures drop quite significantly. They deviate from the theory in quite a significant manner. Nevertheless, you have these stranglers that start appearing all over the place that actually are worse, potentially than the theory. And this is sort of part of the argument. Now, the one above ends up being fundamentally the same, because then now what you do is you look at the floor. Now that I have the temperature of the gas, okay, and I put a convective heat transfer coefficient, so I have the heat flux to the floor, so I can calculate the burning rate. So basically what you do is, the heat flux to the floor, that's the heat of pyrolysis times the burning rate, you divide by the heat of pyrolysis and you can get the burning rate. Okay? So he picked up from Kawagoe all the burning rate equations, and you can present them in exactly the same way and effectively get also the burning rate of the fuel. Okay? Not only you have the temperature, but you have the rate at which you consume the fuel. So if you know how much fuel you have, you will have the time of the fire. Is that okay? So Margaret Law used to work with Philip Thomas, and she turned this into an engineering correlation. So she basically took the problem and said, well, if you want to create then a design fire, given your ventilation factor, let's say 20, you can get the maximum temperature, let's say 900, and you will assume that that temperature will remain constant until you burn out. Okay? How do you calculate the time to burn out? You get the total fuel that you have divided by the burning rate. Now, the burning rate, they took straight from Kawagoe. You know, this is a data from Kawagoe, this is regime 1, this is regime 2. And effectively what you have is they correlated it. Now, you see that there is one term that is missing here, which is the total surface area. Now, obviously, you can introduce that because this is kilograms per second. So if you want to have burning rate per unit area, you divide by the total area and you get kilograms per meter squared per second. Okay? So it's exactly the same ventilation factor. Okay? So this is a burning rate by Kawagoe, and so that gives you, as a function of the ventilation factor, it gives you the time to burn out. So if I go back, what is A0? A0 is the area of the opening that I calculated to do the Bernoulli of the orifice plate. The square root of H0 is the height of the opening, okay? That again I obtained from doing the Bernoulli of the orifice plate. And A is the area through which you are losing heat, you know, which is effectively the area of the compartment minus the floor minus the openings. Now, obviously, all these experiments were done with a single opening. Okay? So clearly, you have to do a little bit of averaging if you have multiple openings. Now, obviously, the area, A0, is not a problem for averaging because it's the area through which the flow rate goes through. So I just add all the areas, and that's not a problem. But for H0, which is the velocity, effectively the height is the one that dominates what is the magnitude of the velocity. So if you have a very big opening that is extremely flat, you will get very little velocity. If you have a very small opening that is extremely vertical, you will get a big velocity. So when you find the average H that you have to input in here, the most precise way is to get a weighted average by the area. Okay? In other words, you get a bigger influence of the bigger areas and a smaller influence of the smaller areas. But there's no correct calculation, there's just simply an average. Yeah?
Or would it be better to weight the square root of the height? Take the average?
Absolutely, yeah, absolutely. So it will be basically weighing the square root of the height, yeah. Because that's the velocity, so what you're weighing is the velocity. I agree. Completely agree. So, but it has to be an averaging that is the most representative of what you want to achieve, okay? So anyway, so that gives you the design fire. So now we have our design fire, and that's the solution that Margaret Law provided. So some people believe that that is too onerous. So the fact that we are assuming the maximum temperature for the entire duration of the fire is very conservative. So in the 1970s, Peterson and his colleagues, they basically published the data. So they compiled all the data that Kawagoe had done, that Thomas had done, and the one they themselves had done. And they said, well, why don't we just simply use the temperature versus time curve as per the data? Okay? So if you look at the maximum number here, this peak will be the transient. And only when you get to the end, for the longest duration, this will be Thomas's number. You can see that the factor is exactly the same, is the ventilation factor. But in this case, the Swedes decided to turn it around and use the proper ventilation factor instead of the inverse ventilation factor. But nevertheless, the factor is the same. So it's the same data, the same type of analysis. The only difference is that Thomas's number will be this one, the one on top. So here, if you go for a ventilation factor of 0.02 and you flip it upside down, so basically you get, it will be 2/100, so it's 50. Okay? So if you go down back to this and you go for somewhere around 50, you get a value around here, around probably 600. So it comes out a little bit taller in here. But basically, Thomas's number in principle should be somewhere around here. Now, this number here, the 50, 100, 150, 200 to 50 is the amount of fuel that you have. So effectively, the fire becomes longer and longer and longer and longer as you increase the amount of fuel in the compartment. So these were translated into the Eurocodes, and they're now labeled the parametric curves. So somebody put an equation that describes these plots and effectively converted them into an equation that people can use, and that's basically comes out from the data. Okay? Now, one of the really interesting things here is the cooling time. Okay? Now, everybody's interested in the heating. Nobody cared about the cooling. Okay? So I left it here as just an arbitrary line. Okay? Now, when this was done, okay, the cooling was done erroneously. Okay? Because keep in mind that these are temperature versus time. And they were using very big thermocouples. Okay? So what they are presenting there is a radiative exchange between the thermocouple and the wall. So effectively, this cooling curve is not the cooling of the gas phase, it's the cooling of the solid. Okay? So if you were to do a heat transfer calculation, can you use these temperatures to calculate the heat transfer during cooling? No, because it's already done for you. Effectively, this is already the temperature of the solid. Okay? The real gas phase temperature is ambient. The fire actually dies and it falls pretty much straight down. So if you have a tiny thermocouple and you have radiation correction, you will get pretty much ambient, because the gas phase, as the air cools very rapidly, so the air is actually cold. But if you have a very thick thermocouple that is in radiative equilibrium with the solid, what you're measuring in that thermocouple is actually the temperature of the solid. Okay? So effectively, if you use this decay to do a heat transfer calculation, you're making a mistake. Okay? And many people do that they effectively take this plot and they use it to calculate heat transfer to the solid. Now, the problem with that is that it creates a very onerous situation, because if you think about it, you are between 800 and 600 for another hour and a half. It's a massive amount of energy that you're transferring, but that massive amount of energy was never transferred there because there's no more combustion. It's simply that the solid is cooling very slowly and your thermocouple is still measuring the temperature of the solid. Is that okay? So you have to be very, very careful, okay, when you actually use this type of data, so you use it correctly. Yes?
So, are we using these still for structural evaluation, or are we using the temperature of the
Yeah. So most people use this temperature here as the input for an H, T hot minus T cold. And therefore, they cannot get the right answer because they're getting too much energy into the structure and the structures are failing. But they're failing on cooling. Okay? Because they're doing the heat transfer incorrectly. Now, instead of actually thinking a little bit and doing it properly, what they start doing is saying, let's put a probabilistic distribution on the amount of fuel load. Okay? and they start shrinking the fuel load. So if you put sprinklers, that basically means I can reduce the fuel load. If you put a detection system, that means I can reduce the fuel load. I'm not joking. So if you actually use all the reduction factors of the Eurocode, you can go from 250 to 12.5. That's 20 times a reduction. Okay? On the basis that the fuel load is a probabilistic distribution, and as I start adding all these measures of protection, my probability of doing damage decreases. I mean, even Harmony will be revolving in his grave, you know, by looking at that. Because obviously that's what he tried to do with sprinklers. But in the case of sprinklers, at least it makes some sense, because the sprinkler does reduce the probability of having that event. Okay? But smoke detectors? So let's just leave it there because I'm going to get angry. Okay? So effectively, you know, this is a ventilation factor, and it's exactly the same principles. Now you can go even more sophisticated and get data and get the heat fluxes directly, or get temperatures and all the stuff, and we can go endlessly with this. Okay? But the problem really is regime 2. Is the fact that we have no idea what regime 2 is, but the bottom line is that nothing works for regime 2. Now, these are the traveling fires, and so these are generally more the type of regime 2. So effectively you have a fire that cannot fill the compartment and it's just literally moving from one side to the other one. It is still a fully developed fire, but is momentum dominated. Okay? So you can have also the growing fires, and you can see a fire that starts in the corner, you know, and as it starts growing, it doesn't have time to burn out, and it continues to spread. Until eventually it's going to fill the entire compartment. And there you get basically, again, the flashover or the fully developed sort of regime 1 Thomas compartment fire. Is that okay? Now, this is data. So this is not a numerical simulation, by the way. So this is experimental data for this type of experiments. So some of you might have seen this. This is a Malveira fire test, and basically shows the evolution of one of these fires from regime 2 to regime 1. Okay? Oops. So this has been burning for about 4 hours, and basically here's your fire. It's consuming all the fuel and it's traveling through a compartment. Okay? So we tricked the experiment by changing artificially the ventilation factor. How did we change the ventilation factor? By changing the value of A. How did we change the value of A? By having the ceiling burning. So the moment the ceiling is burning, then effectively you've changed the ventilation factor because you've reduced the value of A. So we move from regime 2 to regime 1. Okay? So when you get to the middle of the compartment, you can see this line. This is more or less the middle of the compartment. You can see how the smoke layer starts descending. You can see the spread accelerating. And you get this very stable smoke layer descending. You see flashover just happened? feel the excitement. After 4 hours waiting for this to happen. So you see the difference between the two regimes? It's quite dramatic, no? So the problem here is that while they're extremely different, through the years, people have been trying to adapt this model almost to the point where it almost has become, a joke. And so this is the SFP guide for fire exposures to fire elements. And the one thing that I wanted to point out here is effectively is all about the ventilation factor. So ventilation factor only works for regime 1, and basically it meant to give you the boundary condition for a structure. And as you can see, it's a function of the ventilation factor, and the original limitation was that the ventilation factor had to be approximately greater than 18. Okay? In other words, there's a line, where the, where the theory works. Okay? So that was the original design, and that was Margaret Law's method to try to do the design fire. Now, with the years, we move away from Law, and we start creating exceptions. So effectively, we move for a different range, and we start applying, Magnusson and Thorlander extended it to this number. Then you went even further, and now you went to 345, and that was T.T. Lee from another Canadian. And then you kept going and going and going and going and going. You have an endless list of people that have been extending the application of this. I mean, why? Because really it is the only way we can solve this problem in a purely theoretical way. So the ventilation factor is still the dominant parameter that we're playing with. And it basically provides a very simple answer that is very fundamental with very good assumptions and very clear limitations. Okay? And the simple design methodology was developed to provide a worst case scenario, which is the steady state case, and for the purpose of structural analysis. So the problem is that complex problems require complex solutions, and then this is when we run into CFD. So I'm going to go very rapidly, through this, because basically the only question here that we have is trying to understand if CFD can give us what we want. Okay? Now, the problem with CFD is that you have a very complex coupling in the case of fire that requires you to be able to solve all these things. And all these things have very complex time scales and very complex length scales that are very difficult to resolve. So to be able to get the heat transfer, everything has to be resolved appropriately. Okay, so you're going from the micrometer scale of the flame thickness all the way to the meter scale of the compartment. And if you're dealing with forest fires, you're going to the kilometer scale. Okay, so you have a very large range of scales that you need to be able to resolve. And unfortunately for heat transfer and air entrainment, which are going to control fuel degradation, gaseous chemistry, and all this stuff, you need to be able to resolve all these scales. Now, this is a very interesting approach that Stephen Pope, he gave the hotel lecture at the Combustion Symposium and in Warsaw, and he explained the problem of computational models for combustion. And he said there is no universal model. Okay? There are cases where you have very complex turbulence and very simple chemistry, where you're going to focus purely on resolving the turbulence in detail, and you're going to sacrifice the variables associated to the chemistry. And there are cases, like in perfectly stirred reactors, where effectively you can simplify and model in a very simple way the turbulence so that you can focus on the chemistry. But there is no way you can do both at the same time. So he described different types of models in this chart that was basically the complexity of chemistry and the complexity of turbulent flow. So he will place a turbine engine falls in this space, so this is the type of model that I'm going to use. A car engine falls in this space, and this is the kind of model I'm going to use. A waste incinerator falls in this space, and this is the kind of model I'm going to use. The problem with fire is that if, for example, you look at a problem like a tunnel, Okay? If you have a fire in that tunnel, what is going to happen is that you are going to get smoke that is being produced. Eventually, that smoke is going to start moving, and your means of protection is to turn on the fans. So you're going to have fans that are in here that are going to create a complex turbulent flow, because you're blowing air against the buoyant flow of the fire, so that you can actually push the smoke in this direction and people can evacuate appropriately. You have to be able to predict how to push the smoke away. Okay? Now, once you start pushing the smoke away, if you're trying to model the fire, close to the fire, you're going to have very complex chemistry, but probably the flow is going to be laminarized. So you have a very simple representation of turbulence that will fall in category number 1 of Pope's models. Okay? If you want to then model the top where the smoke starts impinging on the ceiling, then you're going to have probably very complex chemistry, but also very complex turbulent flow, because the flow has now accelerated and you have this natural convection buoyancy driven turbulent flow that is incredibly heterogeneous. So it's not that you have an homogeneous turbulent flow, you have a very heterogeneous turbulent flow. So you don't have the capacity, you know, to model this. With this model, you have to go to a different type of model, which is a model that has complex turbulent flow and complex chemistry. Now, if you go to here, then you have no more chemistry. So effectively, you can simplify the chemistry completely, but you have incredibly complex turbulent flow, because it is the stagnation point between the flow of the jet fan and the buoyant flow. And the interaction between the two of them is incredibly complicated from a turbulent perspective, but there is no chemistry. Okay? So I can keep going. If I go to the tail, I might have an intermediate level of complexity on turbulence, so I can do something fairly simple, and I still have no chemistry. And little by little, I can put all the different types of systems and effectively, for example, get to 5 and 6, where effectively the flow is so simple and there's no chemistry that you can actually do Bernoulli. And Bernoulli will be more than good enough. So effectively, you can only solve this type of problems if you do a hybrid model, where you are literally taking advantage of the best parts of each component in such a way that you solve the situation. The problem is that you cannot use a single model. And so when people are trying to use, for example, FDS or any sort of the CFD models to model a tunnel, what they don't recognize is that to be able to get the tunnel right, you need to get the pressure drop in the tunnel correctly. To be able to resolve the pressure drop, you need to resolve the friction in the tunnel. Okay? And the friction in the tunnel depends on the boundary layer thickness. So your mesh has to be millimeter size to be able to resolve properly for the boundary layer and get the friction out of the turbulent model so that you can actually create the pressure drop. Unfortunately, your tunnel is a kilometer long. So if you have a millimeter cell grid to be able to get your friction, all of a sudden you get millions and millions of cells, and you cannot solve the problem. Even then, if you put that size of cell, you will not be able to use something like LES, because unfortunately, LES requires to operate at the scale of the big eddies, the large eddies, and these ones are much smaller than the large eddy. But even then, you cannot resolve the chemistry, because the chemistry is still 2 orders of magnitude thinner than the boundary layer. So even then, you create all sorts of problems, because you have to be able to resolve all these characteristic length scales. So doing computational models, brute force in this kind of systems, is not right. You have to do it in an intelligent way. Okay? And this is a real problem. These are your time scales, these are your vertical scales, your horizontal scales, and depending on where you are. So this is, for example, for forest fires. And you can see the ranges. We go from 10,000 meters all the way to 0.0001 meter. Okay? And you need to be able to resolve all those scales. So brute force CFD is not for fire. Okay? Now, people have done interesting approaches by which you actually, for example, create a sub-model for the fire that then, on the basis of the heat release rate and the diameter, that then you can use as a source input into a much more sort of weather type sort of problem, in which, again, it is the hybrid nature of the model what enables you to work this out. So these are very common for forest fires. So Rodman Lynn and all the people from Sandia Albuquerque developed all these models in which effectively they're treating the fire more as a source and actually doing a CFD model that is more of a weather type model with very large cells, and the fire is fundamentally just a source. And they use experiments and very sophisticated scaling techniques to be able to integrate one model with the other, okay? So the way they do it is the same principles that we have done of the alpha T squared. We're using exactly the same approaches to flame spread, the same approaches to heat release rate, that effectively then we're inputting as a source into these large-scale weather models. Now, this was done a few years ago with FDS5. It hasn't been done with FDS6, but it should be done because most likely you get the same results. When you try to basically understand if the models can do the job, very rapidly you realize that you're in trouble. So this is a case of a very simple fire in one compartment that was very, very heavily instrumented, and the results were not released to the modelers. So the results were withheld, and a round robin was done blindly. Okay? So effectively, all these modelers modeled the problem, delivered the results, and when we received the results, we released the data. Okay? So what you get is that if you look at the range of data that was delivered, this is temperature as a function of time. So you get the people that got it completely wrong in the sense that they got it very low. You got the people that got it completely wrong in the sense that they got it very high. And apparently you got a few people that actually hit the temperature pretty much right. Okay? But then you start looking at the heat release rate, and some of the people that actually got it right, they really got it wrong. Okay? And then you look at the descent of the smoke layer, and the people that were very high, now they're very low. So as you start looking at the details of the data, effectively nobody got it right. Some variables they managed to predict, other variables they got wrong. The same people that predicted one variable right were not the same that predicted another variable wrong. And you can keep analyzing all the data, and you start realizing that effectively nobody got it right. And the ranges, for example, this is temperatures as a function of height, and you can see the ranges go between 800 degrees and 60. So it's not that they got it sort of right or sort of wrong. They got it completely wrong. Okay? So this set of analysis sort of motivated a group of people to launch a whole initiative to try to do this validation and verification of models in an independent and blind way. So the International Association of Fire Safety Science, has this group now that effectively is delivering experiments that are idealized so that people can start testing their models against them. Everybody seems to be able to do a burner. Okay? The moment that you move away from the burner, all of a sudden we start running into all sorts of trouble. So the question is, are the models not good enough? And the truth is that I think it's more the modelers. Okay? Because the problem is a misunderstanding of what level of precision you should be having, and a misunderstanding of what level of precision is necessary. Okay? And that's the key. Okay? In this particular type of problems, maybe going into this level of detail is probably completely unnecessary. And the fact that we're getting it wrong is probably just a function of a reality that the problem is too complicated. But nevertheless, if we look at it in a more intelligent way, we probably can come up with the right estimates to deliver the information that is necessary to be able to design buildings properly. So, despite the precautions, tests of this nature provide little insight to improve models because there's too many variables. So effectively, people are doing big efforts to try to deliver these things, but it is just too complicated. Okay? So right now, our fire models are not really ready for validation and verification tests. You have to work step by step, and right now we are at the level of the burner. Okay? So we haven't been able to go much further than that. To improve fire models, it's necessary to develop a very detailed experimental database, and that's one of our biggest problems, because most of our data doesn't have enough diagnostics. So we haven't measured sufficient things to be able to validate the models properly. So there's a real need to do experiments in this space if we're going to try to validate CFD, and we don't have those experiments, and those experiments, unfortunately, are very expensive. Okay? So we really have to be quite careful about it. So what's next in this field? Clearly comprehensive fire models will not be a viable solution, so the brute force CFD is not going to work right now. We need really a fundamental understanding of the processes that underpins the design of buildings so that we can formulate solutions that are consistent with what we need. So at the end, simplified formulations need to be specifically designed for the purpose of CFD in trying to scale up fire. So I gave you a handout of a paper that is called Scaling Up Fire that describes all this process in detail, so you get a sense of what I mean by all that. So that's the end of the story. So what is the message at the end? So fire in itself is a problem of immense complexity that nevertheless is a problem that we need to solve on an everyday basis. So the real conflict in fire is the fact that the complexity of the problem is incredibly inconsistent with the pace at which the system is evolving and the needs of the system. We don't create our problems. We just basically have to respond. Somebody is going to change a building, somebody is going to change an aircraft, somebody is going to change something, and we need to constantly respond to that. And the problem is that because we have to constantly respond, we're always behind. Our problems are always more complicated than the tools that we have to solve them. So effectively, we always appear to be prehistoric. So we always appear to be behind everybody else. The people that are doing laser diagnostics, they're measuring millimeters. None of those laser diagnostics can be applied to fire. The people that are doing CFD are doing DNS at a level that is extraordinary, with a level of complexity of the chemistry that effectively is impossible to apply to fire. So while we appear to be prehistoric, we actually are not. We just have a problem that has completely different characteristics. Now, what is the value of understanding combustion in here? It is not about being able to model or predict or get the details of combustion. It's being able to understand what matters in that combustion process so that then you can eliminate combustion and formulate a solution that is simplified at a level that is consistent with the need. So once you have that, then you can deliver a solution to the problem. It's not a problem to be behind. That's the way the field is designed. That's the perception part of the system. We are always going to be behind. We always have to catch up because the bar is going to constantly be moving. We don't drive the bar, we just chase the bar. Okay, which is very different to other areas of combustion where the progress in combustion drives the progress of an engine. Okay, in our case, the engine forces us to adapt to the changes. And we always have to be behind, and that is perfectly fine. That's the way it is. We just don't have to allow things to go so far that then we start missing things to the point that we create disasters. So effectively, it's about keeping your eyes open, being conscious of what the objectives are, understanding what are the tools that you have available, and then make sure that you use them in a way that is effectively an honest and safe way, transparent, where you are showing exactly what you know, what you don't know, and clearly establishing this is a level of conservatism that I need to have to make sure that we deliver a solution to the problem. So I hope that you found the last 5 days interesting. It's been actually quite an exciting 5 days for myself. I think it's been really enjoyable to argue with yourselves, and I do hope that you're going to walk away of here thinking that you know a little bit more about fire. So thank you very much for the last 5 days. Thank you.